Um, so, hello everyone. We're very pleased to have our first speaker, Sophia Zomerdijk-Russell, who's a PhD student in the Space and Atmospheric Physics group at Imperial College London. Sophia's research focus is on getting to grips with Mercury's dynamic space environment as the BepiColombo mission flies to the innermost planet. So over to you, Sophia.
Thanks. As Jasmine just said, I'm Sophia Zomerdijk-Russell. So I have actually just submitted my PhD thesis. So this is a nice break to just summarize everything, or try and summarize everything I've done so far in my PhD on investigating magnetospheric dynamics driven by the solar wind at Mercury. So I'll just quickly give everyone an introduction to Mercury's magnetosphere, and then look at two sort of big work topics that I looked at. The first of which is solar wind driven induction, and how we can actually use that to probe Mercury's interior. And then the second one is looking at reconnection processes on Mercury's magnetopause as well. And then I'll finish with some conclusions. So as I'm sure you're all very, very aware, Mercury is the smallest and the closest planet to the sun. So we have this very unique system. So Mariner 10 made 3 flybys in the 1970s, and this led to the global discovery of an unexpected discovery of a global magnetic field, which, like Earth, is produced in Mercury's liquid iron core. And this magnetic field structure protects Mercury from the solar wind, and we form this bubble of a magnetosphere around the planet. And the sort of skin of this bubble is known as the magnetopause. So in 2011, Messenger then became the first spacecraft to enter orbit around Mercury, and actually characterized quite a weak and very northwardly offset dipolar field at Mercury. So due to Mercury's very close proximity to the sun, we actually have this very tiny magnetosphere that's extremely strongly driven by the solar wind. Messenger only performed or had a very strong northerly bias, so we still have quite a lot of open questions about the Mercury system. So thankfully, in 2018, the BepiColombo mission was launched, and it's going to provide this fantastically comprehensive study of Mercury with its 2 spacecraft, Imperial and Mio. So in the work I was doing my PhD, I was using messenger data in preparation for BepiColombo to try and aid in our understanding of this electromagnetic environment around Mercury. So I'm going to first talk about how we can actually use the solar wind to understand Mercury's interior with electromagnetic induction processes. So as the solar wind flows over a magnetosphere, charged particles are deflected in different directions, and this starts to generate a current along the magnetopause boundary. And this magnetopause current can then generate its own magnetic field, which permeates through the magnetosphere. But if we have any variability in this magnetopause current sheet, we can actually start to produce this time-dependent inducing magnetic field. And this inducing magnetic field can start to generate currents on the interior of Mercury, which in turn can generate their own induced magnetic field. So the idea is if we fly a spacecraft through the magnetosphere, we'll not only be measuring the intrinsic field of the planet, but also these 2 time-dependent inducing and then response induced magnetic fields. And if we can actually accurately disentangle these 3 fields from one another, we can work out the electrical conductivity of the material that the current was actually generated in within Mercury's interior. Also, the frequency of the inducing field will determine at what depth those currents are generated in, with much lower frequencies probing to lower depths within the planet. And previous work has been done at Mercury to locate the top of the iron core using these low frequency signals on timescales of a Mercury year. So what I wanted to do was understand the ways in which the solar wind can actually drive the magnetopause variability, and hence how we can actually alter that inducing field, and also what frequencies we're seeing it varying on that could actually allow us to probe to different depths within Mercury's interior. So there are 2 main ways the magnetopause can be altered. The first is the solar wind ram pressure that's going to push the magnetopause boundary closer to and further from the planet. And the second is the interplanetary magnetic field variability, which could actually change the flow of the current along the magnetopause. So we know that the solar wind drives the magnetospheric dynamics in the magnetopause. So we wanted to investigate the characteristic solar wind conditions at Mercury's orbit. So we actually turned to Helios data. So this was taken during a similar phase of the solar cycle that BepiColombo will actually arrive at. So we're looking at solar wind conditions that BepiColombo is maybe quite likely to actually see. So the three panels from the left to the right here are showing the solar wind conditions on different days, but around Mercury's orbit location. And across the top in pink are ram pressure time series, and underneath those are components of the interplanetary magnetic field and magnitude as well. So if we just directly compare these different time series, we can immediately see there's just a lot of variability. Sometimes we see large changes from fairly steady states that are reflected in both the IMF and the ram pressure. And sometimes we just see big spikes in the ram pressure, not reflected in the IMF at all. So we also then took power spectra of these time series, and we find that there are no consistent frequencies again, but actually we have this fantastically broad range of signals, and this is perfect for induction processes. So this has kind of shown us that the solar wind is highly variable and extremely unpredictable in Mercury, so we would need some sort of upstream monitor to actually be measuring the incoming solar wind. But what we can do in the meantime, before Bepi gets there with that upstream monitor, we can actually do some modeling in the meantime. So we first wanted to investigate the impact of variable ram pressure conditions on Mercury's magnetopause inducing field, because it's actually very easy to capture in current magnetopause models of the Mercury system. So I went on and modeled the effect of a changing ram pressure on the motion of the magnetopause and the magnetopause field. So on the left, we chose quite a low ram pressure of only 15 nanopascals, and then a slightly higher 25 nanopascal to see how the magnetopause's field across Mercury's surface is affected by these two different ram pressure conditions. So here we're actually just looking at the Z component of the field. But we can really clearly see that the field is strengthened quite significantly around the kind of day side by that lightening of the blue. But actually, we don't get that much variability around the night side. And this is telling us that the magnetopause's field that's actually generated in response to these variable solar wind ram pressure conditions is non-uniform across Mercury's surface. To then further investigate this, we choose 2 points on the magnetopause surface, one at the subsolar point and one at a point to the south of that. And we input the time series of the ram pressure variability that was seen by Helios at these 2 points. And we generate these time series that are shown in the middle here of the changes in the magnetopause's field at these 2 points. And this kind of gives us actually an example of that time-dependent inducing field spectrum that a spacecraft could potentially measure as it's flying around the system. So again, it's clear that it's non-uniform at these 2 points, so the responses at 2 points are different. And this is actually quite important because this is something we should be considering when we're modeling induction, because usually we tend to assume it's a uniform inducing field because that's just simply easier. But at Mercury, we're clearly showing that it's non-uniform, so it's just something to be a bit careful with when we actually model induction at Mercury. Again, in the electromagnetic sounding of a planet, this broad spectrum of frequency signals is really ideal for producing this profile of conductivity through depth. So we define a transfer function from the observations of the solar wind driven inducing and then that induced magnetic field. This in turn can be used to derive that apparent conductivity through depth of the planet. So in the power spectra of our inducing field signals, these frequencies are peaking between about 10 to the -4 to 10 to the -2 hertz. And our co-author Daniel Hayner actually determined that these sorts of frequency signals should be penetrating into Mercury's crust and mantle. So rather than actually getting down to the core, they're actually going to be stopped in the crust and mantle. So actually we could get a much better idea of what the electrical conductivity of Mercury's crust and mantle is from these sorts of measurements. So the first study, we looked at these ram pressure conditions driving magnetopause variability, but there's also a lot of variability in the interplanetary magnetic field as well. So we wanted to investigate, does the IMF also have an impact on the magnetopause's inducing field? And can we also use these sorts of frequencies signals for induction processes? So in the second study, we wanted to assess if the IMF direction has an appreciable impact on the magnetopause current and the inducing field. So we performed some analytical modelling to find the global impact of the IMF on the current flow along the magnetopause. So here on the left, we're looking at the magnetopause from the direction of the sun. And as the clock angle rotates in that bottom right inset figure, we see that this whole current flow structure is perturbing quite significantly across the magnetopause surface. And this is particularly the case at Mercury because the IMF field strength is much more comparable to the intrinsic field of the planet. So the current flow is actually impacted much more than any of the other planets in our solar system. To then find the impact this has on the inducing field, we approximate this entire current sheet as a current loop around the equator using the approach of Glasmer et al. And then we tilt this loop using the direction of the current at the subsolar point. And we find that while this does actually impact the inducing field, it's not necessarily a dominant effect. So it's quite difficult to disentangle this from other magnetospheric dynamic phenomenon. So if we actually wanted to use these signals for induction processes, we need much better models and much more advanced to actually be able to extract that inducing field response. So in 2025, BepiColombo is going to enter orbit around Mercury with its two spacecraft, MPO and MEO. So this configuration here, where we've got MEO upstream of the planet while MPO is orbiting the planet, is going to be really ideal for determining the impact of that external solar wind forcing on Mercury's magnetopause that MPO is then measuring. So we can use this sort of configuration to determine what sort of wind variability MEO has seen has then resulted in those inducing and induced field signals that MPO is measuring. So we, of course, really hope that Bepi is going to be able to further investigate using timescales of variability that we're seeing in this work as induction methods for probing the interior electrical conductivity structure of Mercury through to the mantle. So our work on induction in the Mercury system showed that IMF should be carefully considered in the context of external forcing and magnetopause, but further modelling is required if we want to actually utilise those signals. But the inducing field that is generated in response to extremely variable ram pressure conditions is something that we should be able to use and to actually provide this profile of conductivity through to Mercury's mantle. So I've spoken about how we can use the solar wind variability to understand Mercury's interior using electrical induction processes, but solar wind variability doesn't just drive induction at Mercury. It also drives this extremely dynamic magnetosphere as well. So the next question I wanted to ask in my PhD was, under what conditions does reconnection actually occur at Mercury's magnetopause? So from measurements, we know that Mercury's magnetosphere is highly dynamic and total reconfiguration actually takes place within just a few minutes. So like Earth, this reconfiguration of the magnetosphere is known as the Dungy cycle, where we have magnetic reconnection on the day side, magnetopause at a location known as the X-line. And at Earth, this is typically when we have a southern IMF and reconnecting with the northerly directed intrinsic field of the planet. And reconnection is happening between the IMF swooping over the planet and the planet's own intrinsic field. And the inflowing solar wind plasma push these field lines together, they reconfigure their topology, and plasma gets accelerated away from the X-line. And this results in these open field lines that have one end connected to the solar wind and the other to the planetary field. And then these get convected into the night side and transport flux into the lobes. But the Dungy cycle is not as simple as it appears, and sometimes these open field lines can actually become twisted into structures known as flux ropes. And it is thought that these are maybe generated during multiple X-line reconnection between the IMF and the magnetospheric field. So flux ropes play this really essential role in magnetospheres. For example, they actually transport that magnetic flux from the day side to the night side, therefore contribute to flux circulation within the Dungy cycle. And as a result, they are quite often referred to as flux transfer events, or FTEs. But for us, since FTEs are this consequence of reconnection, the study of them can actually reveal the occurrence and properties of reconnection within the magnetosphere. So we see FTEs and messenger data. So in the figure on the right, we've got the magnetic field components measured by messenger across the top. We then see messenger crossing the magnetopause at the red dashed line. And then the zoomed in panels underneath are showing the clock angle, magnitude of the field, and then the component of the field that is normal to the magnetopause. So to find an FTE, we look at the magnetic field data for this bipolar signature in the field component that is normal to the magnetopause surface, coinciding with an enhancement in the field intensity towards the center of structure. And that's highlighted by these red and blue vertical lines. So at Mercury, from the messenger observations, FTEs have actually been found to be only a couple of seconds long. They're separated by a few seconds and often appear in extremely large numbers. And actually Observations by our co-author, Weiji Sun, found about 70,000 of these in the messenger data. So They did find that some of these were under northward IMF, suggesting or hinting at that possibility that instead of that southward IMF that we would expect at Mercury and at Earth, we might be able to get some low shear reconnection happening as well. But we wanted to then investigate where do these FTEs actually form and what are the conditions like specifically at the reconnection site that FTE formed at. So we chose about 200 FTEs to model that were associated with these steady solar wind conditions where that clock angle in the upstream solar wind was not varying too much. This allowed us to then actually model the possible locations of the formation of that reconnection, or possible formation locations of the FTE. So we took an observed FTE from the messenger data and we placed it at the location it was observed on the magnetopause boundary. So this is this black dot in the figure on the right, and we work out where this FTE could have come from. So this FTE is essentially this parcel of plasma, and the foundation for tracking is a competition between the magnetosheath flow that wants to pull the FTE away from the subsolar point at the center, and then the magnetic tension forces that want to snap this FTE on field lines away from the reconnection site. So because there are two outflows from a reconnection site, there are two places the FTE could have come from. So we calculate these de Hoffmann-Teller velocities, and then we step backwards in time along the magnetopause to find out where that FTE could have come from. So in this case, the FTE that was observed at the black dot could have formed anywhere along those two cyan lines. But the model does also have to, of course, account for uncertainties in our upstream solar wind. So with MESSENGER, we can't simultaneously know what the solar wind conditions were doing when we actually observe that FTE. So there are a few things that can affect these path locations. These include the orientation and the magnitude of the interplanetary magnetic field and the velocity and density of the upstream solar wind as well. But what we can do instead is get a maximum minimum separation of our formation paths under these different IMF orientations by taking minimum and maximum values of these parameters from previous estimates. And we essentially end up with this, where the FTE that was observed at the black dot could have formed anywhere between both the magenta and cyan lines on either side on the left here. And the final thing we can actually also do is use the polarity of that normal component of the field to give us information on to which cusp the FTE is actually connected. So based on where the FTE was observed and the orientation of the field with respect to the de Hoffmann-Teller velocities, we can actually determine which of the paths going away from the reconnection site is more feasible. And this is actually an approach of Rob Fear et al. So we end up with these most feasible paths on the magnetopause that the FTE could have formed anywhere between. So we then applied this model to 201 FTEs and made some figures like this. So here we're looking at the magnetopause from the direction of the sun for a minimum, a mean, and a maximum IMF orientation observed in the region upstream of the magnetopause by MESSENGER. And the color map is showing this shear angle between the reconnecting fields across the magnetopause surface. So that's between the draped IMF and the intrinsic field of the planet. And the orange is indicating these high shear regions, which is typically where we would expect reconnection to occur, certainly based on what we see at Earth. And the purple regions indicate low shear. So this one was actually making a lot of sense. So we've got these cyan paths that do take into account these uncertainties in the solar wind, passing through these orange high shear regions, and our FTE could have formed anywhere between the cyan lines. So we find a maximum shear of about 165 degrees. So potentially this is the most likely place that FTE could have formed. For then each of our FTEs modeled, we find the minimum and the maximum shear angle that any of the cyan paths pass through. And we repeated this for all 201 FTEs. And this is the figure that we generated. So we've got minimum maximum shear angles along all of the possible formation paths. And we see that for most of our FTEs, we have these shear angles that are above about 135 degrees in the top right of the figure, which is what we would be expecting based on what we know from Earth. But what was really interesting was in the bottom left of this figure, we actually have a few FTEs where the absolute maximum shear angle that was determined along any of our possible formation paths was less than 80 degrees. And this is much lower than we would typically see at the Earth, and actually suggests that reconnection may be happening away from these anti-parallel field configurations that we would typically expect to be favoured. So this is actually the model of the FT that had the smallest maximum shear angle along its formation path of only about 59 degrees. And we can really clearly see from here that none of these formation paths are passing through maximum shear regions that we'd expect them to. So instead, we're passing through these very low shear purple regions on the magnetopause. And actually on the left-hand side of this figure, or on the left-hand side of the slide, we can see that this FT was actually not a one-off. So we modeled the one in blue, but there were actually about 17, I think, other FTs observed in the same path. So this would actually suggest that it's not local conditions. It is something, we are actually forming these FTs under these very low shear northward directed IMF. And this is much lower than we would typically observe at Earth. But we do know that reconnection is favoured for low plasma beta environments. And at Mercury, the magnetosphere plasma beta is very low. So we would actually expect that this reconnection should happen more easily at Mercury than at Earth and under these low shear angles. So that was great. This is what we actually observed. And it was really nice to sort of confirm that we can have really low shear reconnection happening. So in this work, we had presented evidence of this low shear reconnection on Mercury's days and magnetopause, suggesting that reconnection might not actually be confined to these points of maximum shear, and supports the hypothesis that we had this enhanced reconnection-driven formation of FTs that occurs over a much wider range of shear angles than we would typically see at the Earth. So that was a lot to take in, but that was an overview of some work I did in my PhD. So in the first studies, we were looking at solar wind-driven induction processes in Mercury's system, finding that variability in solar wind ramp conditions could actually be utilised for electromagnetically sounding Mercury's interior through to the mantle. From more recent work, we found that FTs form over this really wide range of shear angles at Mercury, with some forming extremely low shear as well. And yeah, of course, all this work has been done in preparation for BepiColombo. So we are really, really excited to see this dual spacecraft actually and utilize that to help us understand even more about the tiny dynamic magnetosphere of Mercury that is so strongly driven by the solar wind. Thank you so much.